Welcome to a course on the working principles and applicability of symmetric and asymmetric ciphers. The module will focus on examining diverse components of cryptographic systems. Let's begin with a short introduction. Before we can move on, we must understand what information theory means. This field was developed by Claude E. Shannon, who you can see in the picture. Shannon is the author of two of the most seminal works on information theory, a mathematical theory of cryptography and a mathematical theory of communication, which was published soon after the first book. Shannon first coined the word bit. A bit is defined as the smallest information unit required to encode one of the two values, 0 or 1. We'll come back to this later. The other term Shannon used is entropy. Entropy is the smallest amount of information needed, on the average, to encode an event. There's a set of probable events for which you need to determine information entropy. The more improbable or unlikely an event, the bigger the entropy is. If you roll fair dice, the entropy of the probability that you will get a 1 is quite small. The number of total outcomes is only 6. On the other hand, in lotto games with the draw results of 5, 15, 23, and so on, the information entropy is very high because the probability of winning is extremely low. There was a huge number of possibilities. Our task in cryptography is to maximize entropy. Let's start with a simple example. Let's take a look at a short script that we'll launch in a moment. This short script is designed to calculate the password entropy in bits. We'll have to calculate a logarithm for multiplying two values. The first variable, range, specifies the range of possibilities determined in the definition. If a password can, for example, only be expressed in uppercase, the range of this will be 1 to 26. The second variable, number, specifies the length of our password. Since the desired result should be in bits, we'll divide it by the logarithm from 2. Next, we'll call the previously mentioned simple function for some of the passwords. The first password uses 8 uppercase characters. The range is 1 to 26. The second case allows passwords to use lowercase letters. The third password is again limited to uppercase only, but password length is doubled. The fourth password uses both uppercase and lowercase letters and a relatively secure number of characters, 16. Let's now find out the true entropy strength of the individual passwords. The first password is only 38 bits strong. You should see entropy as indicative of the secrecy of something. The bigger the entropy, the more secret or improbable something is. Your password should be as secretive as possible for everyone except yourself. 38 bits is not a good strength. In the second case, there are 46 bits. It's more, but the difference is not likely to matter. 8-character letter-only passwords are not secure. 16-character uppercase passwords provide security level for modern computer systems. They amount to 77 bits of entropy. The last password is 93 bits strong. This means that even if you have a 16-bit password that contains both uppercase and lowercase letters, you still won't get over 100 bits of entropy. When we'll be talking about algorithms, we'll show you that algorithms that make use of a key with a length similar to the result we've got provide no security. The passwords are not really secure. They should be more complicated. Before we move on to discuss algorithms, symmetric algorithms in particular, we'll need to explain two terms. The first concept is confusion. Confusion measures a nonlinear relationship between the plaintext, the ciphertext, and the key. It describes the dissimilarity of the ciphertext and the plaintext and the difficulty of extracting information about the key from the ciphertext. This is a vital concept. The bigger the confusion, the more immune to the linear approximation cryptanalysis your cipher will be. The second crucial term is diffusion. Diffusion specifies the distribution or spreading of the plaintext information in the ciphertext. Caesar's cipher diffusion was 1-to-1. The letter A always represented the letter D. The diffusion was practically non-existent in that case. We'd like the plaintext information not to be distributed to one fixed position in the ciphertext. Rather, it should be spread all over the ciphertext. Diffusion is measured by the probability of the successful differential approximation.